Welcome to the pre-calculus notes for Essential Skill E4, arc length and sector area. So much easier. Easier than what? Well, easier than using degrees, because we're going to use radians. Here are some formulas. We have arc length, we have sector area. Theta is the angle in radians. That's worth highlighting. Maybe even draw some stars next to it. That angle must be in radians, otherwise the formula doesn't work. Then r is going to be the radius of the arc. In geometry, recall that the radius of the arc is really the radius of the circle that the arc is a part of. Let's look at a simple example. We have a radius of 5. We're looking for the arc length intercepted by an angle of 2 radians. Well, that's trivial if we use the formula. I want to take an intuitive approach, and maybe you can see why the formula is what it is. Let's start with a circle, and the radius is 5. Here, recall the definition of a radius, a radian angle. A radian angle is the angle that intercepts one radius length worth of arc. So here is one radius length worth of arc, that's 5. Here's another radius length worth of arc, that's 5. So here is our angle. The arc length is simply 5 plus 5, 2 times 5. That's total arc length is 10. If we look at the formula, all we're saying is that arc length is the number of radians, 2, times the radius length. Literally 2 radius lengths. So that is an intuitive interpretation of our formula. When the numbers aren't as friendly, we won't be able to do it quite as intuitively, but this is a nice illustration. The formula is very straightforward. Sometimes there's a little bit of a twist when we bring in an application. So take a moment, read through this, see if you can solve it. The first thing we always do with an application problem is try to sketch the situation. So here is a nice blue Earth. But we're really interested in this satellite. This is not to scale. But here's the satellite's orbit. Earth, we're told, has a radius of 3956 miles. And the satellite is in a circular orbit 200 miles above the surface. So what that's going to do is add 200 to the radius. So this is plus another 200. So that's the twist in this problem. The real radius of the satellite's orbit is 3956 plus 200, which is 4156 miles. We're given the angle. We're going to rotate through 10 radians. And so, how far does it travel? That is the arc length. And that's it. That's all you need to do to find the answer. Since we're given the angle in radians, it makes this formula easy. Here's another example that involves vehicles, traveling vehicles. We have a pebble stuck in a wheel. The wheel has a radius. The pebble travels 2/3 of a revolution. We want to know how far the vehicle travels. Vehicle travel seems like a linear measure, and so at first you might not recognize this as an arc length problem, but it actually is. And here's why. Here's a wheel, and let's suppose we have a pebble right here. As the vehicle moves forward, the vehicle travels, but the pebble rotates along with the tire. What you can see is that as the tire rotates, the distance that the vehicle travels is the same amount that this pebble rotated. If we get to 2/3 of a revolution, this arc length that the pebble really traveled on is the same as the distance that the vehicle traveled, the linear distance. Once we realize that this is just an arc length problem, we can use the formula. We know the radius is 18 inches. We just need theta. Well, theta is 2/3 of a revolution. What's a full revolution in radians? 2 pi. And so theta will be 4 pi over 3. So the arc length is going to be 4 pi over 3 times 18 inches, which is going to be 24 pi. That is not a very relatable number, so we're going to break out the calculator. The answer is about 75.398 inches. That's still a little bit unrelatable, and so I think we'll convert it to feet. Here's another possible application. Speed. If this vehicle is traveling 30 feet per second, we might care about the angular velocity of the pebble. So, what that really means is how quickly is the angle changing? How many radians per second are we rotating through? So, to figure that out, we isolate our time that we're considering to 1 second. In 1 second, we travel 30 feet. As we saw, this is an arc length as well as a distance. The distance corresponds to the arc length. The radius is still 18 inches. However, since we're dealing with feet per second, not inches per second, we should convert this to feet. So in 1 second, how many radians did we rotate through? Well, now it's just a simple matter of using the formula. And there it is. That's how fast we're rotating. Take a look at this example of sector area. With this in the formula, you should be able to figure it out. But be careful, there's a nasty twist in here right up front. It has to do with the angle. Try it out. First, here's our area formula. But there's a stipulation on theta. It must be in radians. We can do one of two things. We can go through our conversion proportion, or if you've been practicing your unit circle, you know that we're talking about this angle. And we know that that is also 3 pi over 4. One way or another, theta is now converted to radians. Now we can find our area. Since we'll typically have calculators for application problems, the easiest thing is just to go ahead and type it in as is. Don't forget, the fraction template can be very useful in making sure that everything's typed in correctly. Remember to use the actual pi button for maximum accuracy. And there's our answer. Don't forget, units for area are squared, so this will be square feet. Now that we've taken the formulas out for this for a spin, I'd like to demonstrate why this is an easier method than what we did in geometry. Here's the formula we used in arc length for geometry. Look at that, much more complicated. Now, it's actually pretty easy to show why our formula is equivalent. And we have to look at what this original formula meant. Theta over 360 meant what fraction of the circle are we talking about? What fraction of the circle is the arc covering? So it's a fraction of a circle times the circumference formula, which you may recognize. So this is what fraction of the total circumference. To describe this in radians, well, remember that a full revolution is 2 pi. So this fraction would tell us how much of the circle we're using in radians. So I'm going to take that geometry formula and rewrite it in radians. And look what happens. Like magic, the 2 pi's cancel. And we're left with exactly theta r. We can do the same thing with the area formula. Remember that the area was, once again, the fraction of the circle that we're dealing with times the area formula, pi r squared. In radians, we get to simplify it a little bit. Once again, 360 degrees is equivalent to 2 pi radians. Only the pi's cancel this time, so it's not as much fun as the arc length. But we are left with theta over 2 times r squared. And another way to write that is 1/2 theta r squared, which is our standard radian formula for sector area. So that's how we got these formulas. Thanks for watching.